Welcome back. In today's episode, we'll discuss affine transformations, which are ways to move objects around in space, scale them, shear them, rotate them. And to do that, we will use the backbone, the mathematical backbone of it. It's matrices. So we will first explain how matrices work and then see how to apply them to get affine transformations working. So let's get started. Okay, so let me go to the next step here. Okay. So let's start with matrices. So recall last time we talked about vectors. Let's just quickly recall those. So a vector, we have a Cartesian system, we have x and y, we had maybe a point here, P, and then we can connect that point to the origin, and we had vector A. And we could write this vector A as the components of A, which are this. So this was AX, and this is AY. All right, so AX and AY. So this was the way we wrote vectors. Now, let's say we want to move this vector around. Let's say we want to maybe rotate it by an amount, by 90 degrees, okay? So let's say we want to rotate this vector. How can we rotate the vector? Well, we can imagine we can rotate the x and y axis system, and if we rotate that, the vector will rotate along with the basis. So let's try to do that. So let's say we want to rotate again 90 degrees. So this will become our new vector x. So this is x, and this will become our new vector y. So vector y and x, okay. And our new a vector will be, well, about this. So let's say that, and then about here, okay. Okay, so this will be our new vector A. Let's draw it like that. So let's call it A first. And this is a 90-degree rotation. So 90-degree rotation. Okay, so how can we describe this kind of movement? How can we make it work? Well, to do that, we can use matrices. So what's a matrix? It's really a table of coefficients. So let's see. So we know from last time that a vector is really a list of scalars. So in this case, AX and AY, these are just two numbers. The vector is a list of them. So a matrix is just a list of vectors. So we can write it like this. In this case, we will write a 2 by 2 matrix because we will have a number here, A, B, C, C, and D, okay? And this will just be a 2-row, 2-column matrix. So it's a 2 by 2 matrix, okay? And what these things contain? Well, let's draw the transformations that we wrote here to the left. So what we want to write is where the x-axis is going after the transformation in the first column, so here, and then in the second column where the y-axis is gone in the first reference system. Let's actually do that. It's easier to see than explain. So the x first vector, you see it's in the original coordinate system is 0x, so it's 0 here, and 1 in y. So this is the new x first vector. And then the y first vector in the original system, it's x minus 1, okay, and y 0. So this matrix here is describing our rotation by 90 degrees to counterclockwise. Yeah, counterclockwise. All right, so how do we then find out what is the A first vector? Well, the A first vector, it's really the matrix. Let's call this matrix A big A, okay, like that. It's really this matrix times the original vector A, okay. So A first is the original vector multiplied by this matrix. So how do we actually do that, that multiplication? Let's maybe define some numbers so that we have them here. Let's say this is maybe 3 and this is 2, just because. Okay, so we have a vector A, right, the matrix 0, 1, minus 1 and 0, okay, right, 0, okay. Then we have vector A, which we said is 2, 3. So how do we go about doing this multiplication? Well, we will get a vector out of it, so the same shape as this one, a column vector. And what we do is we multiply the first row by the first column. So this is the first row, first column, and then the second row by the second column, which will go second row, first column. So, and it's this position here. All right, so let's do that. Let me actually spell it completely so you can see it better. Okay, so 0 times 2, 0 times 2, minus 2 times 3, all right? So actually minus 1 times 3, okay? And then the second row is 1 times 2, 1 times 2, plus 0 times 3, 0 times 3. Okay, so this is our new vector, so this goes away, and we get minus 3, and we get 2. And indeed, if we go and look, so this is vector A first, and if we go and look at what we expected, this matches out because we have this, it's minus 3, and this would be 2. So this is the same vector rotated by 90 degrees is correct. So we now have a way using matrices to describe rotations in space. Now we will see later on how to do other types of transformations, so not only rotations, but before we do that, I want to explain a little bit more about how we can use matrices in general so that we can now then understand it and use it to our advantage in Rhino and Grasshopper. So to do that, let's go and draw a system of equations again. Sorry, a Cartesian system again. So let's do that, x and y. And let's say in this case we have some lines. Okay, so maybe we have this, which is y equals x. And then we may have, let's define some coordinates so that we have a reference. Okay, 1, 2, 3, and 4. Okay, and we can draw another line maybe. So let's do it, maybe this going through 3 and 2. So this line would be minus 3 over 2, x plus 3, the intercept here. Okay, so this is we have two lines now. And the question is, do we know and can we find out what this point is? And the answer is, of course, we can. We can use a system of linear equations. But why I'm talking about this system of linear equations? Well, because we can use matrices to solve this problem as well. And I want to show you how to do it so that then we can do it again in Grasshopper and in Python and take advantage of this kind of calculations. So let's solve it by hand first, and then we'll do it in code. Before talking about transformations, there are other types of transformations, not only rotations, but also movement, shear, and scaling. All right, so let's write the two equations, y equals x, and then we have y equals minus 3 over 2x plus 3. And then I want to rearrange this so that I have all the x's in the first column, all the y's, and then all the known terms. So this is minus x, because I moved it to the left, plus y, which stays where it is, equals 0. We don't have anything left to the right of the equal. And then we do 3 over 2, because we move this minus to the left, x plus y equals, in this case, we are left with this 3 to the right of the equal. So we have 3. I can't write 3. Okay, 3 here. You can notice here that we have a column of x's, so right here, and a column for y's. And we have coefficients in front of each of the variables. So we can actually rewrite this system as the coefficients, so minus 1, because this is minus x, then 1, this is just 1y, then 3 over 2x, and then 1y again, multiplied by x and y, okay, and equals 0, 3. And if you try to use a matrix multiplication rule as we did before for this matrix and this vector, you will actually get this same equation. So this is just another way of writing it, the same thing. And we can, in general, usually call this A, this is called X, and this is usually called B. Okay, so A times X equals B is the typical linear system you would solve with matrix notations. So let's actually now find out what X is. So X would be just, well, the inverse of A. So the inverse of A times B. So what is the inverse of A? Well, we know that we have this transformation we were talking about before that we used to move the vector A to rotate it 90 degrees to the left. Well, the inverse matrix, and we found out that this A matrix is what does it. So the inverse matrix would be the matrix that takes A first and brings it back to A. Okay, so there's a way to do that calculation, and we will do it right now. And it turns out that in case of linear system, that inverse matrix is the way to find out the vector of unknowns given a known vector. So you see, you could imagine this is the same as A as we got before, and this is really A first, okay? So we already know the target vector in this case, and we want to find the original vector that multiplied by this matrix gave this target vector. Okay, so this is the same problem we were finding out before. So let's find out what this A inverse is. So for a 2 by 2 matrix is quite easy to compute. It's just 1 over the determinant of A. The determinant of A is just this one times this one minus this one times this one. Okay, so let's do that. So it's -1 times -1, which is just -1, and then -1 times 302, so minus 302. And then we have the original, sorry, uh, the new matrix, which is we take these two and we swap them around, okay? So we write this one at the top and -1 right here. And then we take these ones, we leave them where they are, and we just change the sign. So this would be -1 and -3/2, okay? And then this is our inverse matrix. So let's actually write it in a better form, easier to be used. So -1 minus 3/2, it's, well, 3/2 is 1.5. So this is -2.5, which is -5/2. So this is -2/5, okay, because it's under the denominator. And then we can multiply this to this matrix. So let's do that. So let's write it again just for simplicity. Okay, and then we will also go here. So let's do that. So this is -2/5 plus 2/5 plus 2 is 3/5, right? Yeah, okay, and then 2/5 again. Okay, so this is A inverse. So now we can take this A inverse matrix and multiply it by the vector B. So let's actually write it here directly. Vector B was 0 and 3, if I recall correctly. Yeah, 0 and 3. And this will give us vector unknown vector. So let's do that. So it's -2/5 times 0 plus 2/5 times 3. Okay. And then we have a 3/5 times 0 and plus 2/5 times 3. So in this case, we get a vector which has the same x and y components, but that doesn't matter. So we have 3 times 2 is 6/5, 6/5. And if you want to compute that, let's see, what is 6/5? So 6/6, can we write 6/5? All right, is 1.2. So this is really the same as 1.2 and 1.2. Okay, so, and if we go back to the chart, you can see this, like, this makes sense because this is symmetric and this is just 1.2 x components and 1.2 y components. Okay, so now we know something about vectors, matrices as well, and we can go in Grasshopper and Rhino and see how this kind of stuff works in there. So let's do that. Okay, we are in our Rhino environment, so let's get here. We will do Python later. Let's now do Grasshopper. So if you go under math, you will see there's a thing called matrix, and we can construct a matrix. So let's use this same matrix we used in the example. So to do that, we need to specify the number of rows and the columns. In this case, 2 rows and 2 columns, and then all the values in the panel as a list, as a multi-line data, in order in which they appear. So let's actually do that here, and then I also need to move Rhino here. Okay, so we have them side by side, and we want to write this -1, 1, 3/2, and 1. So this is -1, then 1, so first row, and then you go back, you go down to the second row, so 3/2 is just 1.5, and then 1 again. Okay, we can drop them in the values, and now you can use, again, matrix, display matrix, to see that displayed in in Grasshopper, and here you have the same matrix. So let's also write this 0 and this 3 vector. And we already know how to write vectors like in 3D with this component. We saw it last time, but we can also write a matrix, like a vector, using the matrix tool. So if we want to do calculation, in this case, this would be a matrix which has, well, 2 rows. So because we have 0 and 3 as rows, and just 1 column. So let's do 1 column over there, and the values are 0 and 3. Okay, so this is just another matrix. Let's display that. And indeed, it's just a vector 0, 3. So can we now solve the same system in Grasshopper? Well, yes, we can. We have this matrix invert matrix component. So here we have invert, and we want to invert matrix A. So let's actually write some notations so it's easier for you to understand. Scribble, scribble, and spell today. Scribble, okay, here. So this is matrix A. This is vector B. And then we want to find out matrix A to the power of -1. Let's say it like this, okay, A minus 1. So we take this matrix here, and this gives you the inverse of the matrix. So let's go there, and you get the same result as we got, hopefully. Let's go see A minus 1. It's this, so minus 2 over 5, which is minus 0.4, 2 over 5, this is 0.4, then 0.6 and 0.4. So this makes perfect sense. Let's move Python away for a second again. And then we can use this A minus 1 and multiply it by the vector, which you just use the same multiplication as you use for numbers. So you have the matrix A, and you multiply it by vector B, okay, sorry, A minus 1. And what we expect to get is 1.2, 1.2, and indeed we do. So this is just the same thing we did by hand, and we wrote a linear system of equations in matrix form, and then we found out the solution of this matrix, of this linear system in Grasshopper. So that's fine. Other tools we have with matrices is swap rows and columns, which just moves rows and columns around. That's not particularly useful in our case, in our application. And then transpose matrix. What is a transpose? I'll show it to you with this because it's very easy to understand. It's basically taking the rows and making them columns. So you see the first row became the first column. Yeah, okay, and the second row here became the second column there. Yeah, that's just the meaning of the transpose matrix, which is useful in some situations, which we won't see today. Okay, so let's do the same thing in Python because we can. And to do that, I'll make use of a package called numpy. So if you don't know how to import, how to use external packages, because this is not available by default in Grasshopper, I have put a link in the description or in a card up here so that you can get to a video where I explain in detail how to install external packages in Python. So right now I will assume that you know how to do that. So we will go ahead and go import numpy, numpy as np. Okay, so this is the package we'll use, and then we'll define a matrix. So this is a numpy array, and then 2 square brackets. So this is the first line of the array, and then the second. Let's maybe format it so that it's easier to read, and let's use the same matrix again. So let's say it's well, -1 and 1, and then we have 1.5. In this case, you can actually write 3 over 2. You could do it in Grasshopper as well, but it doesn't matter. Let's go with 1.5 and then 1. Okay, very good. Like that. This is not necessary. It's just for formatting purposes. Okay, and then we go vector B. That is an numpy array as well. So numpy array. Again, we need two rows. So like that. Yes. Okay. And then we have in the first row, I guess, 0. Okay, so 0 and then 3. We can print this just so that you can see that they were correctly created. So let's go print A and B, print, okay. And indeed, this is the first matrix and this is the B vector. So let's now find out what X is. So let's do that. So let's delete this. And we can, well, we need A minus 1. So let's call it A inverse. So to do that, we need to take matrix A and invert it you can't do it directly like this because that's kind of an array and we need a matrix. So in the way numpy works, you just convert this 2D array to a matrix with the numpy matrix thing, and then you can call the .I function on it to invert it. So let's actually print a inverse matrix. All right, and indeed you get the inverse matrix, and then we can just find out x, which is just a inverse times just using the default times symbol, or you can use this at thing, it's the same, and then b. Okay, and then you can print x, and we expect 1.2, 1.2, and indeed we get it. So this is the same thing done in Grasshopper. We did by hand in Grasshopper and in Python. So let's now go to transformations, which are really linked to this kind of concept of matrix multiplication. So to do that, we have a full menu in Grasshopper, which is specific to transformations, which is here, transform, and we will see these affine transformations here at the top, and probably this move transformation and this rotate one as well. We will not see yet this morphs one because these are not linear, so we can't use matrices to do that, and to understand them, you need to know about parametric curves and surfaces, which we will see in a future episode. So we'll get back to this morph transformation in the future. The other thing we want is to use this transform, and you get, in fact, transform matrix, which reminds you and explains you that to do this kind of transformations, matrix kind of have a connection. So let's start with, I guess, with the easier transformation, which is just scaling. Okay, so let's use the scale component, and before we can do that, let's draw something we want to scale, otherwise you can't see the result. So we will just draw a box. So we'll do, I guess, domain box right here, and this will just be, let's define the domain. The domain is really from where it starts to where it goes, the same as you do in math. So let's do -1 to 1 in all three directions. Okay, so we have a box centered in the origin, right? That, and we'll use this to move it around. Okay, just so that I don't see the plane, which I kind of don't like, I will just preview off and then get a box parameter, so I can only see the box in the preview. Okay, it's not necessary, but okay. And then we can take this box. I will also hide that box, and I will go wireframe. Okay, and I can take this, and I can also see now the lines instead of seeing the full box, because I want to see the full geometry only when of the transformed geometry, not of the original one. So I will take this box and put it into the geometry, and you see, because the factor has a preview value as a default value, you already get the result. And this is really a multiplier, a number. So let's say 1.0. Okay, let's also make it get to maybe 2, why not? Okay, and then if you put it into the factor, you will see that if I slide it around, I get the scaling property. And you'll also see that I get the output geometry, which is just a deformed geometry, and I also get this transform, which by default it just says scale 0.6, but if I go to utilities, transform matrix, and I connect this transform to here, you will see I actually get a matrix. In particular, since this is 3D space, I get a 4x4 matrix which describes the transformations, and you see that this coefficient 0.6 is on the diagonal of the matrix. So if I change it, look at the slider value and at the diagonal of the matrix of the first 3 values of the diagonal, and you see this is just a matrix. To scale objects, you just take a 4x4 matrix and you multiply it by, well, the vector that defines each point in space, and then you get the transformed coordinates of the points, and you can use them to rebuild the new box, which is bigger. Why is it a 4x4? Well, it's because you actually get a, let me just take this, okay, just to show you what happens. So you're getting a value, let's go 4, and then this is maybe 1, 2, 3, actually, let's say 0 0.1, 0 0.2, 0 0.3, okay, and then 1. Okay, so this is actually the vector you are multiplying this matrix to. So the first 3 will contain the actual coordinates of the points. So let's say maybe this point is 0 0.5, 0 0.5, 0 0.5. Okay, and then you always put a 1 down here. The reason is because of movement of translation, and we will see that later. For translations, a 3 by 3 matrix is not enough. You actually need a fourth column. So we just put a dummy empty line with zeros here. This is never used, and then this vertical column is used for shift, for transformations, for translation. Sorry. Well, we will see it in a second. So we have scale now, and we saw that the scale goes here, and these 3 coefficients are the scaling in each direction. So we can actually preview this off and use these other components, scale NU, so non-uniformly, and then you can put the box in again, and you'll get a plane or relative to which you want to do the transformation. In this case, we just get the word xy. We're fine with that. Okay, let's connect this matrix again here. By default, they're all 1, so they don't get scaled. But if I take this slider here and I connect a value to x and a different value to y, okay, and then a different value again to z, so let's do that. You see that each direction gets scaled differently, and indeed we get the first element of the diagonal is the x scaling, okay, the second element is y scaling, and then the third element is z scaling, okay, and this matrix is really mapping all this information in a compact way. Okay, so let's now do shear. Okay, so shear is quite simple, so let's hide this scale, and then we can do shear. So shear is this transformation right here. We put in the geometry, then we need a vector, and a plane. So the plane, let's leave it as the xy plane, and that is the plane which will shear transformation will be parallel to this plane. We will see it in a second. The grip is a vector which is perpendicular to this vector, to this plane, sorry. So in this case, it's unit z, because it's just the z-axis, and then the target is where the z-axis will go after the transformation. So in this case, let's define a vector, okay, like that, and we will put x component 1, okay, and y component 1 as well, and the z component 1 as well. Actually, on y we need 0, so like that. Okay, and you see this is shearing along the x component, and if we change the value of x, let's actually put it as a real number with a range up to maybe 2, okay, like that. You see we get shear along the x-axis, and if you put negative numbers in, let's support that, so -2 is the, like that, you see you shear to the other side. And if you change these instead of x to the y, and you get the shear on the other direction. And we can also see the transformation matrix. Where does this number go? This 0.606, it goes in the first quadrant, in this third column and first row. Why is like that? Because we're moving along x, so the first row, perpendicular to the z unit vector, so it's in the third column. And by changing this z reference and this components, you will also be able to like write numbers in this element, this element, this element, this and this, and this will just describe the shear in all the possible directions. We will not see that because it's not necessary. Let's just explain what is this number, because it may not be clear because it's not really an angle. It's really the cosine of the angle. So let's go back to the whiteboard just for a second. Okay, so like this. So let's say we have a vector. Let's draw the axis like this. So x-axis and y-axis. And then let's go 1, 2, 3. Well, actually, we don't need these things. Let's draw a second set of axes. Let's say it's like this, maybe. So this is a second set of axes. So y first and x first. Okay. And then we can project the first axis on the old system, and we can do the same for for y. So it's like, like this. And you will see if this is the angle of rotation, let's call it theta, we can describe these coordinates of this point, so where the x-axis has gone relative to the original coordinate system, and we recognize that this is a square rectangle, square triangle. So we know from trigonometry, a couple of videos ago, go check that out if you don't remind this trigonometry stuff. We know these dimensions, so we know that this, let's assume that the length of x is just 1. So we know that this x component is just the cosine of theta, and we know that this y component is just the sine of theta. And similarly, well, this will be the cosine of theta as well, and this would be minus the sine of theta. So we know now how to like make up a matrix to rotate stuff around. So this generic matrix, it's just the position of vector x, so it's cosine theta sine theta, and then vector y, it's it's minus sine theta times the cosine of theta. Okay, so these using cosine and sines, we can define from angles the position, and we can use this. This is the same as happens in the shear vector. So these same elements are in the shear vector, and indeed, if we put in something that we know, so let's say 0.5, okay, we can get well, actually, if we convert, I guess we can convert we can put an angle in instead of just this number. So let's say we want to rotate by 90 degrees. So we can put the cosine in, okay, like that. And then we have 30 degrees. So 30 degrees, which we have to convert to radians internally. So radians like that. So we get 30 degrees converted to radians. We compute the cosine of it, and indeed we get 0. Well, probably the sinus is the one we want. So let's see. Okay, yeah, the sine in this case of 30 degrees. So if we have a 30-degree rotation, we get here a 30-degree rotation. We get a 0.5 coefficient, which is what we expect. Okay, so now we know about shear as well. Let's see the last transformation, which is under Euclidean move. Okay, there it is. And this move transformation is just a vector. So let's hide this shear. Let's take this transform out. Okay, and then let's write, well, the geometry is always our box we had at the beginning. So let's drop it in like that. And then motion is just a vector, and it's describing like where all the points are rigidly moving. In this case, let's just put in 3 random values. So 1.2 maybe for x. Let's put in the same number at first. Okay, like that. And then let's just switch it a little bit. Okay. And indeed, you can see that these 3 numbers are in the 4th column, as I was mentioning before. And you get like the movement on x, the movement on y, and the movement on z in this matrix. And of course, I did write all these transformations with these components, but you can as well just draw a matrix like with this component, define all these coefficients yourself, and then drop this matrix into a transformation. So let's actually do it for this simple example of translation. So we need a matrix which has 4 rows and 4 columns. 4 rows, 4 columns. Okay. And then the values. The values are, well, first row is just 1, 0, 0, and then 1.2. Second row is 0, 0, 1, 0, and then a 0.9. Okay. And then the third row is 0, 0, 1, and then 2.6, and then 0, 0, 0, 1. Okay, so that would be all the coefficients. We drop them in values and we get a matrix. Okay, and then we can use that to do a transformation. So instead of using these known predefined transformation, we will just do a transform generically, then go to transform and plug that in, and then go to take our box. Okay, and you will see that this box and this box are exactly in the same location. So you can either define your own coefficients and drop them generically directly in this transform, or you can use these, which are easier to understand and remember. Okay, so another thing we can show, I will show it on the transform, but that also works on all the other ones, is inverse transformations. So as we did with the A inverse matrix, you can also do an inverse transform, which guess what it will do? It will just take this matrix, compute the inverse of it, and apply it to the transformed geometry. So let's take this is the transformed, let's say this is the inverse transform, okay? And then we can take the transform component, drop this in, then take this is the transformed geometry, and indeed the inverse transform just takes the transformation and brings it back to whatever it was. And so last thing, before we get to Python and see how this transformation work, is combining transformations, because right now we saw that we can do like movements, we can do shear, we can do scale and whatever. We can also do rotation. I haven't shown it, so let's do rotation as well. So very easy. So let's take our box here. Okay, the plane is that we know, then the radians to get the angle, let's say 30 degrees again. Let's drop it in. This is the rotation by 30 degrees, and let's hide these because we don't like it very much. Okay, and indeed we can get a rotation around the z-axis in this case because the plane is defined as x, y, and then we can also display this transform there, and you see that well, actually rotation is really actually a shear in the same as shear in terms of how you encode shear into the transformation matrix. It's just that with shear you just plug one value, with the instead rotation you plug in these four values. So these are the same four values that we get here. So cosine theta minus sine of theta, and cosine of theta, which you get over here. Okay, so those are the same numbers. So let's actually go to 30 instead of 35. And indeed you get minus 0.5 here and 0.86 here, which is what you expect. 0.86 is the cosine and 0.5 is the sine, which is exactly what you expect to get. So this is the same thing. Okay, let's put them side by side, like minus sine sine and cosine cosine. Okay, so that is just, so shear is really the same as rotation. In particular, I mean, yeah, shear is kind of the same, but you just have one of the coefficients. In this case, you have four, the first 2 by 2 matrix field. So let's now combine these transformations. Let's say we want to do the rotation and then move the object around. How do we do that? You can use, well, these components. You have compound, okay? So let's take this transformation of movement, then we, of rotation, then let's take the transformation of movement here, and we will shift and put it in. So order matters in this case, so let's actually do it better. So with a merge like this, let's disconnect the transform. So we get rotation first, then we get a transform of movement right here. Okay, let's delete this third input. We don't need that. Okay, so this is two combined transformations. And indeed, you will see that you get the rotation plus the translation here. And the way you do it is you just multiply the two matrices together. So let's do that in that way as well. So instead of doing this transform compound, you can also multiply the two matrices together as we did before, but we have to convert this like transformation to a matrix in the terms of what Grasshopper does. So to do that, we go to maths, we go to deconstruct the matrix, and then we reconstruct it again. So we will just take this, this, and this, deconstruct this matrix and build it again. So now we have the same matrix, but written as a matrix instead of a transformation. It's really the same. And we drop it in here, and then we do the same with the other matrix for the translation. Let's put it there, okay. And then the order here matters. So you want to put the first transformation is the last one that you want to apply. So they are in inverse order. So in this case, we have first this and then this. So to do that, in case of multiplication, we have to like make the opposite. So the first transformation is this, which is translation and then rotation. Okay, sorry, the opposite. And if you multiply them together, you see you get exactly the same result. Okay, so now we have this compound transformation. We could just take this transform like this, okay, and put in the transform. Either this one or that one will be exactly the same. Okay, let's use the one at the bottom. Why not? Okay, and then the geometry is just the original geometry. Like drop it in there. Let's hide the component, and indeed we get rotation first. So this got rotated and then it got moved around. And remind that the order matters. So if you switch them around, let's do that. Let's take another multiplication, but let's use the opposite order. And then let's drop it in as well. You see you get a different transformation because in this case we moved first and then we did the rotation, which is different. Okay, so we saw everything now in Grasshopper. So let's now, before we wrap up, see how these transformations work in Python, which is quite simple. Let's create a new Python script. The only thing we need is the input box, so we can move it around. So let's take B, maybe call it the brep, and then go right click and define a type, which is brep here. We don't need the out, and we maybe want bt, which is the transform brep, and t, which is the transformation matrix we use. Let's drop in the brep in the input so that we can get it then. Okay, like that. And let's also maybe hide this transformation. Okay. And then let's go and write a bunch of code. So how do we do transformations? By using the Rhino geometry built-in functions. So let's define a transformation maybe of movement. So let's say movement. We won't show all of them. Maybe we will. Let's say move. Let's start with scale then. So scale, it's just a Rhino geometry. Sorry, we need to import Rhino geometry at first. So let's go import rhino.geometry as rg, so Rhino geometry. So Rhino geometry.transform scale. Okay, and this expects, well, this defines the matrix of transformation. You can put in either a point 3D, or in our case we want the plane and the x, y, and z factors as we did in Grasshopper. So the plane is just Rhino geometry.plane world xy. And then we have the x factor, which is just the Rhino geometry sorry, it's just a number, so it's a float. So let's say 1.5 maybe, and then 1.2 and 0.4. Okay, so this is a scaling operation, and we can also print that scale, and you see you get a matrix, row 1, row 2, 3, and 4. Okay. And then you can define other types as well. So you can go shear, it's Rhino geometry.transform, transform dot shear. Okay, and in this case it asks you for a plane, which is the same xy plane we did here, and then let me recall, the x vector, y vector, and z vector. Okay, so in this case we need 3 vectors then. So Rhino geometry vector 3D. So the first vector will just be 1, 0, 0. We don't want to shear along x. The second vector will just be the y, because we don't want to shear along vector 3D. We don't want to shear along y, so let's go 0. We don't want to move the x, so x and y will stay the same after shear. So 0, 0, 1. And then the z vector, instead we want to move it, so the Rhino geometry dot vector 3D. And if we want to go to 0.5, we said, on x, and then 0 y, and then 1 on z. Okay, so this is the same transformations we got before, and we can print that so you can figure it out yourself by checking the matrix. Indeed, this is the same we got before with this 0.5 in the third element of the first row. Let's then do movement. So movement is just Rhino geometry translation here. And here you just get a vector in, so Rhino geometry of vector 3D, and you get 3 components. So let's say we want to move 1.2 in the x, 0.6 in y, 0.6 in y, and maybe 1.6 in z. Okay, so let's put that in as well. So we have move, put that in. Okay, so we have move. And the last transformation is rotation. So rotate is just Rhino geometry dot transform. Dot transform dot rotation. Okay, so let's say this rotation, and we can put in a bunch of different stuff. Let's see which one we like. I guess start direction, float, rotation center, vector 3D, float, rotation axis. Yeah, let's use this one. So we put in a float, which is the angle in radians. Then we put in the rotation axis. So we will say the Z vector, and then a rotation center, which will just be the origin. So let's say the vector first. We need the convert degrees to radians. So import math. Okay, then we go math dot degrees, I guess, sorry, radians, and we say 30 degrees converted to radians, so that's the float angle. Then we want the vector, which is just Rhino geometry dot vector 3D. Then we go 0, 0, 1, so that's the z vector, and then a point, so Rhino geometry dot point 3D, and that will just be the origin, so 0, 0, 0. Okay, so we have the transformation as well. Let's make it bigger, why not? So you can see it better, and this is the final thing, is rotation, and indeed you get the same matrix we were getting before in Python as well. How do you apply then a transformation? Is you then go to take a brep, so b dot transform. So b is the brep input, transform, and then you pass in the transformation. Let's say we want to pass in scale. brep has no attribute transform. Let's actually go to check the documentation. Why not? So Rhino common, like that, Rhino common API, and then we can go here, search. We go transform brep. Okay, we get here brep transform component. I guess it's this one. Okay, transform applied to Rhino geometry base. It should work then. Oh, I haven't wrote the S in. Okay, transform. So indeed, here we got transformation. Before we do that, let's actually say that BT, so the transform one is the original one, and then transform the copy of it. Otherwise, we will change the original as well. And then you will get, let's say that T, the transformation, is in this case scale. And if you go and check that out, we get the scaling transformation applied. So this is the new object scaled along with the parameters we saw. And then T is the transformation matrix, which you could like drop in and see this in this graphical form. Okay, so let's maybe put shear in just because. So shear, it's like that. Okay. I'm probably there's something wrong with the shear. Let's check. Yeah, okay. So this is the y vector, so like that. Okay. So shear, okay. Then we have movement, and we have rotation. Okay, we have all the transformations we want. And in the same way we did before, we can combine the transformations. So let's say combined. That would be, let's say we want to apply rotation and then movement. And in this case, this is applied first, this is applied second. So they are in the opposite order in which you multiply them. And then you get combined. This is the transformation. This, let's go T, maybe it's the same. And indeed, we get the same rotation and movement. It's different than what we had before because we defined different coefficients, but it's the same thing. All right, so I guess that was it for today's video. It was quite a lot of stuff, so maybe watch it a couple of times to grasp all the content. I hope you found this useful. If you did, leave a like and subscribe to the channel, and see you next time. Bye.